So we're going to talk about linear. Well, really, this boils down to conservation of linear momentum. We see that everything in motion has energy, even stuff that's not in motion. So we know that because energy is conserved, there's a lot of other stuff that's conserved. This is the reason that when an object's in motion, it remains in motion, right? Some of Newton's laws, because there has to be a force that acts upon it. And then we see the relationship between forces and energy when we did our roller coaster work. So for 6.1, we're going to talk about linear momentum. So the definition of linear momentum of an object is the product of the mass times its velocity. So this is a quantity that we measure by multiplying the mass of an object by the velocity. We should point out that because velocity is a vector, that momentum is also a vector, which means it has a magnitude and a direction. And then the unit for momentum is just kilogram meters per second. In other words, there's no fancy name. We don't have a momentum unit, okay? So for a system of objects, the total momentum is the sum of each one. So in my diagram here, I have 3 objects, and this one has a momentum in this direction, a momentum in this direction, and in this direction. All 3 of those objects do. And so the sum of all the vectors will give you a resultant vector of the total momentum. This is important because when we're going to talk about conservation of momentum, this is how when you play pool, if you hit a pool ball with a cue ball, that momentum is conserved, and it's conserved with regards to the vector. So it's like a transfer of momentum. When the cue ball hits another ball, that momentum is transferred from the cue ball to the other ball. Does that make sense? So it's like an energy, but we call it momentum. And so another thing that happens is we have a change in momentum. So if I have this ball here, and it has a momentum and it hits a flat surface, so this is like a pool ball hitting the bumper of a pool table. The angle that it comes in at, perpendicular to the surface, is the angle that it goes out at, because that's the only way that momentum can be conserved. Okay, so I'm jumping ahead and letting you know that momentum is definitely conserved. And so to sum up all the forces, well, not forces, I shouldn't use the word forces, but it's, remember when we summed up the forces to find out what the total forces were and the net force and the x and y, we do the exact same thing, except now we're using mass times velocity, and we call it momentum, okay? So now, if an object momentum changes, a force must have acted upon it. So we said an object will remain in motion. In other words, the velocity will remain the same unless there's an acceleration applied. That's another way to say an object will remain in motion in a straight path unless a force acts upon it. Since the mass doesn't change in the object, the only thing that changes is the acceleration. What does the acceleration do? It changes the velocity. So essentially, if we have this change in velocity over time, which is really acceleration. So think of it like this. We have our force, which is mass times the acceleration, but the acceleration does nothing more than change the velocity in a certain amount of time. We could distribute this mass through to both velocities, and you get mv minus mv naught, which is a change in momentum. And so a change in momentum over time is equal to force. Does that make sense? So if I wanted to calculate the force an object would apply to something, in other words, if I take that cue ball and I hit it, and it hits another ball, I can figure out what force that ball will have on the other one through this mathematical equation. Does that make sense? Okay. So then the net force is equal to the rate of change of momentum. So all these things are connected. So then the impulse is the change of momentum. So I said all that because the force that's generated is called an impulse. So we give that a label, and it's called an impulse. But the impulse is just the change of momentum. So when we say force, the force is actually the change of momentum over time. If we multiply both sides by time, then the force times the time is equal to the impulse. In other words, just the change of momentum. And so typically the force varies during the collision. So I won't get into a lot of details, but there's some things that take place where the force is not, everything is dynamic. It's not static. It's not easy to count 1, 2, 3. As 2 balls collide, believe it or not, the balls actually transform a little bit. Sometimes they stick together a little bit. There's lots of things that take place. So if we were to graph the force over time, you would get something similar to this. Does that make sense? So we can measure the impulse of different things. So if you hit a golf ball with a driver, and we can, the contact times are very, very short, but we don't want to ignore them. And so, like, we need to kind of examine the times too, because remember in our previous slide, we said that the impulse was the force, the average force times the time. So the average force, if you have this graph, is kind of this. That's what the average force is. times the time of contact. So if we go forward here, we see in milliseconds, which is 10 to the negative 3, how much time it takes for the contact between these two objects. So if you hit a golf ball, it's 1 millisecond, or 10 to the negative 3 times 1. At a baseball, it's 1.3 seconds. If you hit a tennis ball, because the tennis ball is a little more malleable, it transforms a little bit more, there's more contact time, so that's 5 milliseconds. If you hit a football, or if you kick a football, because of the way the football is designed, you have longer contact, because when you kick the football, and those of you that have kicked a football can actually kind of feel the football wrapping around your foot. So that's going to be 8 milliseconds. And then in soccer, if you do a header, it's 23 milliseconds. Okay? Does that make sense? So when moving an object, or when a moving object stops, its impulse depends only on the change in momentum. This can be accomplished by a large force acting on it in a short amount of time, or a small force acting on it over a longer amount of time. So if you catch a softball, somebody throws you a really fast softball and you catch it with your bare hands, it will hurt, it will sting. Why? Because that ball has momentum and you have to change it. Okay? Your hands literally stop the ball, but there's energy that takes place. So the heat that you feel in your hands and that impact, that's kind of like a transfer of energy. Does that make sense? That's why it stings. So what we can understand about this, and we do this intuitively, when I jump up, or let me rephrase that, when I jump down to something, so if I were to jump up in the air, or let's say I jumped out the second-story window, I won't. But if I were, when I hit the ground, I bend my knees. And the reason I bend my knees is because it changes the amount of contact time. It changes that change in momentum over time. That makes the transfer a little less painful for me. But the same with when we catch a ball. Anybody who in here plays baseball or softball? All right, if you catch a ball with your bare hand, don't you always kind of move with the ball? Do you ever notice that? So if somebody throws a ball to you, you catch the ball and you move with the ball because you're changing that momentum over a longer period of time, which it doesn't hurt as much. And really, because you're increasing the time, it reduces the force. So if we go back here, let me show you what I mean by that. We said that the force is equal to delta P over delta T. So when I increase the time, it reduces the force. So whatever delta P is, if I go from 4 and I change that to delta P over 8, then this is a lot lower. So this would be less than. Whoops. Because the denominator is a greater value, what I'm doing is I'm lowering that impact force of that ball. When I catch it with my hand, I slow it down. This is the same principle that's applied through an airbag. What does the airbag do? It doesn't apply an equal amount of force to stop your face. What it does is it increases the time, so it gives the force on your body isn't as high because we're increasing the time over the change of momentum. The change of momentum just happens. So if you get in a car accident and you slam into something and your car stops all of a sudden, your body will want to keep moving. If there's something there that stops your body right away, that force will impact your body and you'll hurt yourself. If you use an airbag, what it does is it increases that time, even just a fraction of a second longer, dramatically changes the amount of force that acts on your body. So that's why we have airbags in our cars. So the conservation of linear momentum, just like we learned in the conservation of energy, we see how all these things are related. The conservation of energy, we said the kinetic energy is 1/2 times the mass times the velocity squared. Well, momentum is mass times the velocity. So if we were to multiply your momentum by 1/2 times the velocity, again, you get kinetic energy. So mathematically, you can see the connection between conservation of energy and conservation of momentum. So this is a law, and if there are no internal forces, the momenta, that's plural for momentum, of individual parts of the system can change, but the overall momentum stays the same. So if you play pool, and I hit that cue ball, what normally happens, depending on how you hit the cue ball rolls down the table. As soon as it hits the other ball will move, or sometimes both balls move. And we'll talk about that when we compare elastic and inelastic collisions and stuff like that. In this example here, where we have two masses that have a spring and then there's a wire holding them together, when you burn the spring, or when you burn the string, the spring will expand and that'll force both objects in opposite directions. So in this example, there's no external force, but the individual components of the system do change their momentum. The problem is that when you sum up the momentum, in other words, there's no velocity in the beginning. So so you're going to have your initial momentum here, which so this momentum will be mass 1 times the velocity, which is 0. So your momentum here is equal to 0. Similar over here, we have a different mass times its velocity, but the velocity is 0, so the momentum here is 0. So when we sum up the momentums in this example, we get 0. Now what happens here is that when I sum up these, I'm going to get 0 again, but they're going to be equal in magnitude, but in opposite directions. Does that make sense? So since the masses cannot change, the only thing that differs is the velocity. Okay? So that's why this less massive object has a longer arrow. Remember the magnitude. Remember when we talk about vectors, the longer the arrow, the higher the magnitude. So this has a higher velocity in the negative direction. This one has a lower velocity in the negative direction. And they're proportional too. This is twice as massive as this object, so then the velocity is twice as long and in the opposite direction of that velocity. Does that make sense? Because the momentum's conserved. So, any questions so far? So when we talk about conservation of linear momentum, we also use this for other things too. Momentum is always conserved during a collision to one degree or the other. So here we have a board that is stationary, not moving at all, and we have a bullet. And the bullet has a very high velocity, but a kind of small mass. Well, the wood also has a mass. So when the bullet hits the wood, when the wood shatters, this momentum plus this momentum plus this momentum has to equal this momentum plus this momentum. The momentum of the board is 0 because it's not in motion, but the momentum of the bullet is going to be the mass of the bullet times the velocity. And so essentially, if you add all these up, it should equal this momentum because the momentum is conserved. Now clearly there's like friction and heat and sound, so we lose a little energy to non-conservative forces, but we're talking theoretical here. Okay? All right, here we go. Next slide. So what is the difference then? What happens if the balls, like when you play pool, if they stick together, if they both roll together, if one doesn't roll, how do we define what's going on? So when we talk about that, we classify collisions in 2 categories. One is elastic, the other is inelastic. So in elastic collision, the total kinetic energy is conserved, always. In an inelastic, the total kinetic energy is not conserved. So here's where it starts to get a little tricky. Momentum is conserved, but the kinetic energy isn't always conserved. Does that make sense? And when the total, so this is one way to determine if something is an elastic collision or an inelastic collision. And we'll do a lab of this at the end. We have a virtual lab where we're gonna simulate 2 blocks hitting each other. And what we'll do is we'll calculate the total momentums, the sum of the momentums, and then we'll calculate the total kinetic energy. And then we'll see in one scenario, the kinetic energy, the final kinetic energy sum is not equal to the initial. And so that would be an inelastic collision. And then we'll find out that when the kinetic energy is conserved, and now you might say, well, Mr. Adams, you said the energy is conserved. Well, yes, that's true, but the total kinetic energy is only one form of energy. So remember, we have potential energy, heat energy, there's all types of energy. So in an inelastic collision, some of that kinetic energy gets transferred to another form. Where in an elastic collision, it does not. Does that make sense? Okay. So in a completely inelastic collision, what we have is 2 objects that basically stick together. Okay. And we'll do that. Sometimes that happens. So if we have some really nice videos from the International Space Station where they take 2 tennis balls and I think they put Velcro on them or something. And when the 2 collide, they stick together. When they stick together, there's a certain amount of energy, kinetic energy, that's used up to keep them together. So that's why the kinetic energy is not conserved. Does that make sense? This happens in car accidents sometimes. So when 2 cars collide, if the bumpers get entangled or the cars get entangled in any way, you lose some of that kinetic energy simply because the car uses a bunch of energy to try to overcome that stickiness. And when it can't, some of that kinetic energy gets lost. However, momentum is conserved. Okay? So here we have a more massive object with a velocity colliding with a smaller object. At the point of collision, the 2 become 1. And what happens is we have 1 velocity and 1 mass, which is the sum of the 2 masses. And so clearly the kinetic energy won't be conserved. So the fraction of the total kinetic energy that is left after completely inelastic collision can be shown this way. It really has to boil down to the masses. So if you have the final kinetic energy, that will be kind of proportional to mass of the first object over the initial kinetic energy, which will have the masses of the two objects. Does that make sense? So for an elastic collision, both the kinetic energy and the momentum are conserved. Now, an elastic collision, if inelastic means they stick together, what does elastic mean? That they don't stick together. Okay, so they don't stick together, and what happens is that your initial momentum for the first object and your initial momentum for the second object is completely conserved. So the sum of these two objects will be equal to one another. Same thing with the kinetic energy. Now the velocity is really the only thing that can change because the masses will not change. So what you'll have is, depending on the size of the mass of the object, in other words, if you have a very slow moving object but it's extremely massive and it hits a little ball that's extremely less massive, then the velocity, because it's completely conserved, when you hit that very small object with a very massive object, then its mass can't change, so the momentum is conserved in the form of velocity. So if I take like a big, huge wrecking ball and I hit a BB with it, that BB will go flying very fast. Does that make sense? Okay. Oops, I wanted to delete that. Okay. So here's an example of what Mr. Adams was talking about. I have a very massive object. If I hit a less massive object, the velocity has to increase, and because the masses cannot. But in this slide, what we're talking about is that collisions take place in two shapes. Collisions may take place with two objects approaching each other or one overtaking the other. So in this one, well, let's do the first one. What's going to happen when these two hit, whether it's elastic or inelastic? The overall velocity will be positive, right? So there might be a transfer of velocity to the small ball, right? And this may have less velocity, but clearly both of them are going to be moving to the right. What's going to happen here, though, on this second scenario? They have equal velocities, but this one is much more massive. In fact, it's twice as much as M1. M1 has 2 kilograms, M2 has 4 kilograms. So it's going to overtake. So this red ball will ping back and go. They're both going to be having a velocity in the negative direction. Does that make sense? That's what they mean by completely overtake. Hang in there, guys. We're almost done. So when we go to do calculations of momentum, it's technically there's multiple momentums that are taking place every day. So in order to accurately predict it, what we do is we use the center of mass, and I'll show you some videos of what center of mass is. But if we make predictions of the center of mass, we can always determine where the object will go. Nothing is perfectly spherical, right? So if I wanted to make this calculation of a car, I would pinpoint the center of mass of the car, and then I would figure out what would happen if that center of mass collided with another center of mass, as opposed to trying to figure out, you know, how much mass is in the bumper and how much mass is in the fuel tank and how much mass is in. What I do is I would calculate the center of mass and make my calculations from there. And so when we want to figure out the net force, usually what we do is we take the mass of the whole object, every little point. Technically, we could go down to every little molecule, every little proton if we wanted to, and then calculate the velocity in relative to everything else. But what we're going to do is we're going to take the total mass of the object and consider the acceleration of the object at the center of mass. Okay, so we need to understand what the center of mass is. So one way we can find the center of mass is that you could just hang the object from 2 different points, and where the intersection of the points, because gravity is just going to pull something straight down, and it kind of naturally finds an equilibrium because it's pulling down on every molecule towards the center of the Earth in such a way that it will automatically balance kind of on the center of mass. And so if we take 2 points and suspend an object from 2 different points, the intersection of those 2 points is going to be the center of mass. Does that make sense? I would recommend that you do that with 3 points just to make sure in case you had an error in one of the first points when you measure it up. But that's one way to find the center of mass. The center of mass is not always contained within the object's physical matter. Sometimes the center of mass is outside of the object itself. So if you have a ring, because there's no matter in the center of the ring, our calculations will be based on the center of mass, which is actually located in the center. Same with an L-shaped channel, something like this, the center of mass would be there, outside. So lastly, because momentum is conserved, this is how jet propulsion and rockets work. If I fire a bunch of particles downward and it hits the Earth and the Earth won't move, the Earth pushes back up on the object and it causes a rocket to propel. This is all based on conservation of momentum. Because the Earth is so much larger than the particles, it causes it to propel. A smaller scale example of this is shooting a gun. If I shoot a gun, I propel a very small, massive object, this bullet, away from the gun, but because of the velocity of that object, it pushes back on the gun. Now, because of gravity, I feel it in my shoulder. Whoever, I know some of you guys go hunting. Who's fired a gun before, like firearms? Okay, you know that kickback you feel in your shoulder? That's conservation of momentum. The bullet is going this way, but momentum has to be conserved, so it pushes back on the gun this way. Does that make sense? Same with a rocket. When those gases expand and they push this way, because momentum has to be conserved, the rocket still thrusts forward. So when you're young, we say that you push against the ground and the ground pushes back. But what happens when you're way up high in the air? You're still not pushing on the ground. So as the rocket gets closer and closer to the outer atmosphere of Earth, it's still being forced upward. Well, that's because there's a conservation of momentum. As those molecules thrust backwards, because momentum has to be conserved, the rocket will propel upwards, right? So the expanding gases, because of the chemical reaction and all those things, those molecules go down, but momentum has to be conserved, so it forces the object to go up. Does that make sense? You can use that same principle in airplanes with thrusters, and it's a similar thing, but they use a fan and a reverse thruster just kind of redirects the air, and that's kind of how jets slow down. So you hear about air brakes and stuff like that, or reverse thrust. It's a similar principle because we're redirecting the momentum because it's a vector. If you force the air to go in one direction, then the plane must slow down in the other direction. Does that make sense? So it's the same concept, just backwards. The summary is that the change in momentum over the change in time is equal to your net force. And we can manipulate many of those variables to make predictions about what happens with objects in motion. Impulse is a similar measurement, but basically it's just the change in momentum or the average force times the change in time. The center of mass can be calculated by taking all the initial parts of mass and the distance that they're measured from the center divided by the total mass. And that gives us the actual x location of the center of mass. That's a little more mathematical way to calculate that.